Welcome to iLecture Online. Today we're going to lecture about physics, and in particular we're going to talk about simple harmonic motion. And so simple harmonic motion can be looked at in various ways. So the first thing we're going to do is talk about it in terms of energy. And so what we have here is we have a spring, we have a mass hanging down from the spring, and if we just let it go, just don't touch it, eventually it'll come to a position here of rest, and we call that the equilibrium point, so that this is the zero displacement point of this particular system. Then if we pull the mass down a distance x and we let go, then the system will start oscillating up and down, and of course if there's no loss of energy, it will do that forever. Of course in the real world that doesn't happen. So if we're now supposed to figure out what the position is at any point in time, or what the position or the velocity is at any point in time, we have ways of doing that. So first we're going to talk about it in terms of energy. So we're going to use the energy equation, where energy initial, the energy that we'll put into it by pulling the spring down, and of course we have to do work to elongate the spring, then we will let go, it's going to oscillate back and forth, and the energy that's then contained within the system will be an interplay between the kinetic and potential energy. So energy initial equals energy during the oscillation, and so that will be potential energy. So let me just write it as PE for potential energy plus the kinetic energy. So once we put energy into the system, then there'll be a combination of potential and kinetic energy as it oscillates back and forth. Notice that when it gets to the end points, when it's oscillating, it gets to the very highest point where it stops at that moment, since the velocity there will be zero, all it has is potential energy. Over here, when it's elongated and velocity stops, all it has is potential energy. And then in the middle, it'll have no potential energy. The only thing it has there is kinetic energy. And anywhere else, it'll be a combination of both kinetic and potential energy. So the initial energy we put into it, now the distance that we displace it, the maximum distance is amplitude. So this is x max. That is the max displacement from the equilibrium point. So the energy we put into it is 1/2 kA squared. And that will then always be equal to the combination of potential and kinetic energy, which is 1/2 kx squared plus kinetic energy will be 1/2 mv squared. Now notice, when v is 0, then x will be equal to a. That's at its maximum distance away from the equilibrium point. All right, we're now going to solve that equation for v. So what we want to do here is find out what v is, the velocity, as a function of x, its position. So the first thing we can do is get rid of all the 1/2s, because there's a 1/2 on every part of the term. We now want to solve this for v, so I'm going to move the kx squared to the left side. So we have ka squared equals, or minus, kx squared equals mv squared. Now I'm going to turn the equation around, because I want to solve for v, I want that on the left side equation. So if I turn the equation around, no signs change. So we have mv squared is equal to ka squared minus kx squared. I'm now going to pull out the k, factor out the k, so I have mv squared equals k times a squared minus x squared. And then I'm going to divide both sides by m. So moving the m over here, we get v squared is equal to k over m times a squared minus x squared. Now this k over m is a very special quantity that of course determines the properties of the system. Mass is the mass at the end of the spring, and k is the spring constant. So those two numbers, those two constants, determine how fast this object will be oscillating up and down. And finally, if I take the square root of both sides, I can say that velocity is equal to, plus or minus, but we don't have to worry about that, the square root of k over m times a squared minus x squared. So if you, let's put in the plus or minus, so you can see v is equal to plus or minus, because obviously it can move in a positive direction and it can be moving in a negative direction. And notice that the magnitude of velocity definitely depends upon the difference between the maximum amplitude and the position of the mass. All right, so that is one way in which we can look at the velocity as a function of x. And later on, we're going to show you some examples of how you can plug in certain values for x to get certain values for v. Another thing we want to do is figure out what the acceleration is as a function of position. And for that, we use the equation that the force acting on a spring is going to be equal to minus kx. Again, the minus there is because if you pull the mass out in one direction, the force will be on the spring will be pushing in the other direction or pulling in the other direction. So that's where the minus comes from. And then we have the, of course, old equation, F equals ma. So we know that no matter what, F equals ma always holds true in any situation. If we now set those two equal to each other, we can then say that minus kx is equal to ma, or if I change the equation around, we can say that ma is equal to minus kx. And finally, dividing both sides by m, I have the acceleration is equal to minus k over m times x. And that's the other equation that we need to describe, in this case, the acceleration of a simple harmonic motion situation, like, for example, mass on a spring. So now we have the velocity equation, we have the acceleration equation. We are now ready to start working some examples. Okay, so that was our first introduction.